Good day and welcome to our lecture on group 14 elements, which include carbon, silicon, germanium, tin, and lead. In this group, we have non-metal elements, semi-metals, and also typical metals. Overall, the elements in this group are known as the carbon group elements. These elements have the common electronic configuration Ns2p2, which upon removal of the p electrons would give rise to a +2 oxidation state, or removal of all 4 electrons from the s and p orbitals would give rise to a +4 oxidation state, which is more favorable. Nevertheless, the +2 oxidation state becomes more and more stable down the group. The halides, oxides, and sulfides of the M2+ ions become more and more stable on descending down the group. For example, we have silicon tetrachloride, which is a stable molecule, but when you move down the group, lead tetrachloride is already less stable and decomposes at 105 degrees Celsius. Lead iodide does not even exist, but lead 2 iodide does. And that is due to the 6s inert pair effect, which we have already encountered in the previous group. The elements become progressively more metallic down the group. Only carbon often occurs in its elemental form, and the other elements are mainly found as oxides, sulfides, carbonates, and sulfates, which is due to their lower electronegativity. The coordination number increased down the group, and for example, we have carbon, which is mostly 4-coordinated, giving rise to compounds in which carbon is tetrahedrally surrounded. Silicon, on the other hand, has coordination numbers of 4, 5, and 6 respectively. For example, you have a tetrahedral tetraoxidosilicate, or you have a pentafluorosilicate, which is trigonal pyramidal, and finally you even have a hexafluorosilicate, which is octahedral. Now let's look at the chemistry of carbon, which is a very abundant element. Carbon occurs naturally, and elemental carbon has several allotropes. One of these is diamond, and the unit cell of diamond is depicted here. All the carbon atoms in diamond are sp3 hybridized, and due to the lack of conjugation, diamond is an isolator. It is one of the hardest materials, and it is colorless and transparent. Another allotrope is graphite. Graphite is actually thermodynamically more stable than diamond, and in graphite you have sp2 hybridized carbon atoms, and due to the planar arrangement of the sp2 hybridized carbon atoms, you have electron delocalization, and therefore graphite is a conductor. Due to the sheet structure of graphite, it is also a very soft material, and it is a black material. The individual sheets in graphite are held together only by weak van der Waals interactions. Due to conjugation, the electrons within each sheet can freely move around. Now, if you isolate a single sheet of this graphite, then you obtain graphene. The planar structure of graphene, which is a very interesting material, is depicted here. There are many research groups in the world that are working on graphene, and in 2010, the Nobel Prize in Physics has been awarded to Andrei Geim and Konstantin Novoselov for their groundbreaking experiments regarding the material graphene. Now, if you take one sheet of graphene and you roll it up, then you can have a carbon nanotube. And so the carbon nanotube looks something like this. It is again a single sheet of carbon which is wrapped around to form a tube-like structure. Another allotrope is the fullerene. Fullerenes are named after the architect Buckminster Fuller. They are spherical molecules, which are also known as buckyballs, and they could contain, for example, 60 carbon atoms, which is the Buckminster fullerene, or 70 carbon atoms, or even more. Here you can see a depiction of C60, in which all carbon atoms are equivalent. There are both single and double bonds. Essentially, C60 has the structure of a football, and here you can see the Montreal biosphere, which has essentially the same structure. Hera Kroto, Robert Curl, and Richard Smalley were awarded the Nobel Prize in Chemistry in 1996 for their discovery of fullerenes. Carbon forms 2 compounds with oxygen. The first is carbon monoxide, which contains carbon in the +2 oxidation state. It is sp hybridized and therefore linear, and there is a triple bond between the carbon and the oxygen. Carbon monoxide is highly poisonous. Small amounts of carbon monoxide can be produced in the lab as the anhydride of formic acid by dropping the latter in concentrated sulfuric acid. Here you can see the equation. So as a simple decomposition of formic acid into carbon monoxide and water. Larger amounts are produced via steam reforming or water-gas reaction, which we have seen already in the chapter of hydrogen. The second carbon oxide is the carbon-4 oxide or carbon dioxide. The carbon in carbon dioxide is sp hybridized and there are two CO double bonds. Solid carbon dioxide is known as dry ice. Small amounts of carbon dioxide can be produced in the lab by treating carbonates with acid. So if you treat sodium carbonate with 2 equins of hydrochloric acid, you are creating first carbonic acid, which decomposes to water and carbon dioxide. Larger amounts of carbon dioxide are produced by burning carbon or by the shift reaction, which we have also encountered already. Between carbon dioxide and carbon monoxide, there is an equilibrium which is called Bouduard Equilibrium. So you have graphite, which can react with carbon dioxide to form 2 equins of carbon monoxide. In this depiction, you can see the temperature dependence of the Bouduard equilibrium. You can clearly see that at higher temperature, carbon monoxide is preferred, whereas at lower temperature, luckily we have the preference for carbon dioxide, which is non-toxic. If you analyze this reaction in more detail, then you can see that a solid and one gas is converted into 2 gas molecules. And so this process is entropically favorable. And since delta G is proportional to minus T delta S, it is easy to understand why the equilibrium shifts to the carbon monoxide side with increasing temperature. Another very common carbon compound is methane. Methane has the formula CH4 and it contains the carbon in the oxidation state of -4. In methane, the carbon is sp3 hybridized. It is a gas with a very low boiling point. It is the main component of natural gas, and it is also a greenhouse gas, which is more than 20 times more potent compared to carbon dioxide. Estimated natural gas reserves amounts to about 230 gigatons carbon. Methane is highly abundant as clathrates on the ocean floor, with an estimation of about 500 gigatons carbon. Clathrates are essentially methane molecules that are trapped in ice. And here you can see a depiction of clathrate burning. And here you can see a methane molecule which is entrapped in the structure of ice. And in red you can see the oxygen atoms, and in white these are the hydrogen atoms of the water molecules. Large amounts of methane are produced due to the cattle livestock, and in fact it is estimated that about 18% of the greenhouse gas emission are due to the livestock sector. Silicon is another abundant element in this group. The word silicon is derived from the Latin silix, which means silicious rock. It is the second most abundant element on Earth, preceded only by oxygen. In percentage, that would amount to about 26.3%, which is accessible in the Earth crust. And oxygen, on the other hand, has an abundance of 48.9%. Silicon has very strong affinity for oxygen and occurs naturally only in the form of compounds, mainly as silicates. Technical silicon can be prepared by reduction of quartz, which is silicon dioxide, using carbon at high temperatures of about 2000 degrees Celsius. In the lab, magnesium is used. Here you can see a simple equation. So again, you have solid silicon dioxide, which reacts with solid carbon to give liquid silicon and 2 equins of gases carbon monoxide. High purity silicon for semiconductor applications is produced from reduction of purified trichlorosilane with hydrogen or by pyrolysis of extremely pure silane. Subsequently, the silicon is then purified by the Czochralski process or by zone melting. Here you can see the simple equations again. Trichlorosilane plus 1 molecule of dihydrogen would produce silicon and 3 molecules of hydrochloric acid. On the other hand, you can simply heat silane, which will form silicon and liberates dihydrogen gas. In this slide, we are explaining the zone melting process in a bit more detail. In this process, a polycrystalline silicon rod is melted in a small zone. The melt zone is gradually moved along the length of the rod, and a pure silicon single crystal forms behind the zone upon cooling. Now the impurities accumulate within the melt and travel along the rod. Here you can see the melting zone. So you have this rod here, it is very hot here, and the silicon melts. And as this rock moves up or down, you form very pure silicon, while the impurities will accumulate in the melt and move along with the rod. Here you have a simple schematic depiction. So on this side, you have a single crystal of pure silicon, and in black you can see the impurities that move along the melting zone. And eventually, when you are done, you can simply cut this off, and so you have obtained a very pure single crystal of silicon. In this depiction, you can see the apparatus which is used for the Czochralski process. Here again, you have a silicon seed that assists crystallization. And again, here you have the melting zone. And so this is liquid silicon. And here you pull out a single crystal of pure silicon. So essentially a seed of silicon, single crystal is dipped into molten silicon. Single crystalline silicon that forms on the seed is drawn out from the molten silicon in a rotating fashion. And here you can see the attachment and the growing single crystal of silicon. The pure silicon is then cut into wafers for further applications in the semiconductor industry. In many of its compounds, silicon is tetrahedrally coordinated. Here we see an example of silicon tetrachloride, which contains silicon in the oxidation state of +4, and this molecule is tetrahedral in shape. If you treat silicon tetrachloride with 4 equivalents of hydride, then you can convert this into the so-called silane, which is a gas. On the other hand, you can hydrolyze silicon tetrachloride with water, and that leads to the formation of silicic acid. Salicylic acid can then be deprotonated using a very strong base, such as sodium hydroxide, to form sodium silicates. And in these silicates, you have a silicon which is tetrahedrally surrounded by oxides. Silane, as mentioned, can be produced by the reaction of silicon tetrachloride with the hydride source. For example, you can take lithium aluminum hydride, and that gives rise to the tetrahedral silane molecule, and it eliminates, of course, lithium aluminum chloride. Silane is a colorless gas at room temperature. It is stable in the absence of air or moisture, but it decomposes at higher temperature to form silicon and dihydrogen. In the air, it burns explosively to give silicon dioxide. And again, this is due to the very high affinity of silicon for oxygen. And so in this reaction, you have silane reacting with 2 equivalents of dioxygen to give silicon dioxide, and water is produced as a byproduct. In water, silane decomposes to silicic acid, and this is a simple hydrolysis to form the tetrahydroxide species. And again, dihydrogen is eliminated. In alcohol, you have a very similar reaction, but instead of the acid, you form the silicon with alkoxide groups. In particular, the 2 last reactions highlight a very different reactivity of silane compared to methane. Another very common silicon compound is silicon dioxide. Silicon dioxide is widely distributed in nature in both crystalline and amorphous forms. And for example, you have many minerals, or you have sand, and you have also gems like amethyst. There are 8 different crystalline modifications. One of them is quartz. And in contrast to carbon dioxide, silicon dioxide has no silicon-oxygen double bond. All 8 crystalline forms of silicon dioxide contain 3-dimensional networks of corner-sharing SiO4 tetrahedrons. One of these forms is called beta-cristobolite. This structure is structurally related to the diamond structure. You simply replace the carbon atoms with silicon atoms, and in addition, each pair of silicon atoms is linked by an oxygen atom. Again, you can see the diamond unit cell here, so you can place a silicon here, and adjacent to each of the silicon, you have oxygen atoms. Here you can also see a depiction of amethyst and of quartz. Finally, we can look at the structural diversity of silicates, which are all derived from silicic acid upon dehydration. For example, if you remove 1 water molecule from 2 molecules of this acid, then you can form a silicon-oxygen-silicon bond. And if you continue removing water molecules, then essentially you form silicates. Here we have a monosilicon silicate, which has a simple tetrahedral structure. And you can also have cyclic structures. And here we can see 3 silicon atoms, which are bridged by oxygen atoms. And you can increase the number of silicon atoms and the oxygen atoms, and you will end up with larger and larger cyclic silicates. The tetrahedral silicon O4 units can also be connected into a linear polymer, and also the cyclic versions can be arranged into endless chains which means you will end up with polymeric silicates. Now we look at the chemistry of silicon halides. Silicon tetrafluoride SiF4 can be prepared from the reaction of HF on silicon dioxide. And so you can see in a simple equation here again, silicon dioxide eventually dissolves under the influence of hydrofluoric acid into the silicon tetrafluoride, which is a gas, and 2 molecules of water. And because of this reaction, HF cannot be stored in glass bottles, but must be stored in plastic bottles. Silicon tetrafluoride is a colorless gas, and it fumes on contact with moisture because of hydrolysis. So if you treat silicon tetrafluoride with water, then silicon dioxide reforms, and in addition you form hexafluorosilicic acid. The hexafluorosilicic acid is only stable in the presence of water or as salt. Here you can see an acid-base reaction involving this acid, so it can actually protonate water to the hydronium ion, and then it forms the hexafluoridosilicate anion. In anhydrous form, it simply decomposes under elimination of HF and forms back the silicon tetrafluoride. Silicon tetrachloride, SiCl4, can be prepared from the reaction of silicon and gaseous HCl above 300 degrees Celsius. Here you can see a simple depiction, again very simple. Treatment of silicon with 4 occurrence of HCl leads to the formation of silicon tetrachloride, and dihydrogen is eliminated as well. And so you can know that this is a redox reaction. The molecule is tetrahedral. It is a colorless liquid at room temperature that fumes in moist air due to hydrolysis. So this is very similar to the reaction we have seen before. And again, you produce during this hydrolysis the salicylic acid, and HCl molecules are liberated as well. The halide X in SiX4 is readily replaced via associative substitution at the silicon center. So the silicon center in SiX4 can act as a Lewis acid and accept the electron pair from the donor by expanding its valency. Here we see an example involving the reaction with water. So the oxygen donor of water would coordinate to the silicon to form a 5-coordinate species, and then subsequently you eliminate HCl and you form a tetrahedral species again, which now contains a hydroxydoligand. Now you can repeat doing this 3 more times, and finally you end up with the silicic acid. With this reaction, we have already come to the end of this short lecture.